Welcome! In this video, we'll explore LeetCode problem number 1053, previous permutation with one swap. This interesting problem challenges us to manipulate an array to find the largest permutation smaller than the given one, using only a single swap. Let's dive in and analyze the solution step by step. Let's start by understanding the problem. You are given an integer array, ARR, with a size of n. Your task is to find the largest permutation of this array that is smaller than the array's current sequence. The catch is that you can achieve this by swapping at most one pair of elements. If no such permutation exists, meaning it's not possible to find a valid result smaller than the input, you simply return the array as it is without making any changes. Here, a permutation refers to any rearrangement of the elements in the array. For the input format, you're given an integer array, and for the output, you need to return the resulting integer array that meets the criteria we just discussed. To make this clearer, let's look at some examples. In the first example, the input array is 3, 2, 1. The goal is to find the largest permutation smaller than this array. By swapping the elements 2 and 1, we get the array 3, 1, 2. This is indeed the largest permutation smaller than the input. Now, for the second example, the input array is 1, 1, 5. Here, the array is already sorted in ascending order, meaning there is no way to rearrange the elements to get a smaller permutation. So, in this case, the output is simply the array unchanged. Now, let's consider another example. If the input array is 1, 9, 4, 6, 7, the largest permutation smaller than this array can be achieved by swapping 9 and 7. When we do this, the resulting array becomes 1, 7, 4, 6, 9. This is smaller than the original array but still the largest possible permutation that meets the criteria. Finally, let's review the constraints. The length of the array can range from 1 to 10,000, and each element in the array can have a value between 0 and 10,000. These constraints ensure you handle a wide range of input sizes and values efficiently. Additionally, there are some important edge cases and key points to keep in mind. If the array contains only a single element, no swaps are possible, so the output is the same as the input. Similarly, if the array is already sorted in non-increasing order, like 5, 4, 3, 2, 1, it's already the smallest permutation, so again, you return the array unchanged. When dealing with arrays that contain duplicate elements, you need to be careful to ensure that swaps still produce the largest permutation smaller than the input. Finally, it's worth noting that empty arrays are not valid input according to the problem's constraints, so you don't need to account for them in your solution. To solve the problem previous permutation with one swap, we need to find the largest permutation of the array that is smaller than the given array, using at most one swap. One of the initial approaches we considered was a brute force method. The idea here is to generate all possible permutations of the input array, filter out the ones that are smaller than the original, and then select the largest valid permutation from the filtered results. However, this method has significant drawbacks. Generating all permutations of an array has a time complexity of O(n), which grows extremely quickly as the size of the array increases. This makes the approach computationally infeasible for larger arrays, and it doesn't take advantage of the structure or properties of permutations to optimize the process. Thus, while conceptually simple, the brute force approach is inefficient and not practical for this problem. To address the inefficiencies of the brute force method, we developed an optimized approach that relies on key observations about permutations. First, to generate a smaller permutation, we need to swap two elements such that the resulting array is smaller than the original. To ensure that this smaller permutation is the largest possible, we take the following steps. We identify the rightmost decreasing pair in the array, which is the first point from the right where the descending order is broken. This gives us the index I. Next, we find the largest element to the right of this index that is smaller than the element at I. Let's call this index j. To maximize the result, we choose the rightmost occurrence of this smaller element. Once the indices I and j are identified, we simply swap the elements at these positions. If no such decreasing pair exists, it means the array is already in ascending order, and we return it as is. Additionally, there's an alternative two-pointer variant of this approach that explicitly uses pointers to find the indices I and j. However, this alternative doesn't provide any performance benefit and is slightly more cumbersome to implement, making the optimized single-pass method the better choice. The optimized approach is the strategy we selected for this problem due to its efficiency and clarity. It operates in O(n) time, making it highly scalable for larger inputs, such as arrays with up to 10,000 elements. By leveraging a single traversal to identify the indices for the swap and another to execute the swap, this method is not only fast but also intuitive to understand. When compared to the brute force method, which is computationally infeasible for large inputs, the optimized approach is vastly superior. While the two-pointer variant mirrors the logic of the optimized method, it introduces unnecessary complexity without offering any additional performance benefits. Ultimately, the optimized approach strikes the perfect balance between efficiency and simplicity. By focusing on the rightmost decreasing pair and ensuring the swap creates the largest possible smaller permutation, this solution effectively meets the problem's requirements within the constraints of O(n) time. In this problem, we're tasked with finding the largest permutation of the input array that is still smaller than the original array, using at most one swap. If no such permutation exists, we simply return the original array. To solve this, we start by identifying the rightmost decreasing element. This means traversing the array from right to left and finding the first index, I, where the element I is greater than I plus 1. This step is crucial because it pinpoints the first position where the array stops being in decreasing order from right to left. If no such index exists, it means the array is already the smallest possible permutation, and we can directly return it as is. This forms the foundation of our approach, ensuring we identify the right spot to make a swap that decreases the value of the array overall. Once we have identified the index I, the next step is to find the largest element to the right of I that is smaller than I. This requires traversing the array from I plus 1 to the end and locating the largest possible value, j, where j is still less than I. This step is key because swapping I with the largest smaller element ensures that the resulting array is as large as possible while still being smaller than the original. If there are multiple candidates for j that satisfy the condition, we choose the rightmost one. This choice guarantees that the resulting permutation is the largest valid option with just one swap. Finally, we perform the swap between I and j, giving us the desired result. The array is now the largest permutation smaller than the original, and we return it. Here, we rely on the input array itself for in-place modifications, which minimizes space complexity. The algorithm is efficient, with a time complexity of O(n). This comes from the single traversal to find I, followed by a second traversal to locate j. The space complexity is O(1), as no additional data structures are used. To understand this better, consider the example of the input array, 3, 2, 1. First, we find the rightmost decreasing element by traversing from right to left. Since A1, A2, we identify I equals 1. Next, we look for the largest element smaller than A1 to the right of I. The candidate here is A2, which has the value 1. These steps ensure we correctly prepare the array for the final swap. After identifying the indices, we perform the swap between A1 and A2, resulting in the array 3, 1, 2. This is the largest permutation smaller than the original array, so we return it. Now, consider a second example with the input array 1, 1, 5. In this case, when we traverse from right to left, no I plus 1 is found, meaning the array is already the smallest possible permutation. Since no swap is needed, we simply return the array as 1, 1, 5. These examples highlight how the algorithm handles both swap required and no swap scenarios efficiently, ensuring correctness in all cases. This implementation solves the LeetCode problem 1053, previous permutation with one swap. The goal is to find the largest permutation smaller than the given array, using at most one swap. The implementation begins by finding the rightmost element that is larger than its next neighbor, indicating the first position where the array stops being in decreasing order when moving from right to left. This is done with a reverse loop, and if no such element is found, the array is already the smallest permutation, so it is returned as is. Once this element, indexed as I, is identified, the next step is to locate the largest element to the right of I that is smaller than I. This ensures that the resulting permutation is the largest possible while still being smaller than the original array. The search is done in a forward loop from I+1 to the end of the array. After identifying the element to swap with, we exchange ARR, I, and the identified element. The final array is returned as the result. This solution efficiently solves the problem in O(n) time, where n is the length of the array, as it involves a single reverse traversal and a forward search for the swap candidate. The algorithm handles edge cases where the array is already the smallest permutation or where no valid swap exists. Here, we start by defining the prevPermOpt1 method, which takes an integer array ARR as input and returns the modified array. The goal is to find the previous permutation of the array with exactly one swap. First, we determine the length of the array and initialize a variable I to help locate the rightmost element that is greater than its next element. This is done using a loop that iterates backwards, starting from the second to last element. If such an element is found, we break out of the loop. If no such element exists, meaning the array is already in its smallest permutation, we simply return the array as it is. Next, we move on to find the largest element to the right of ARR, I, that is smaller than ARR, I. This ensures we achieve the largest possible permutation that is still smaller than the current one. We use a variable maxIndex to keep track of the index of this element, updating it whenever we find a better candidate. Once the appropriate indices are identified, we proceed to swap the elements at I and maxIndex. This is done by temporarily storing the value of ARR, I, in a variable temp, assigning the value at maxIndex to ARR, I, and then setting ARR, maxIndex, to temp. This single swap modifies the array to become the previous permutation. Finally, we return the modified array as the result. This implementation ensures that we achieve the desired permutation in an efficient and clear manner, adhering to the problem's constraints. Here, we begin with the array 3, 2, 1, and our goal is to find the lexicographically largest permutation that is smaller than the current array. The first step is to identify the rightmost point where the array decreases. Starting from the second to last element, we check if an element is greater than the one to its right. At index 1, we see that ARR 1 is 2 and ARR 2 is 1. Since 2, 1, we find our breakpoint at index 1. Next, we need to find the largest element to the right of this index that is smaller than ARR 1. Looking at index 2, which is the only element to the right, we find that ARR 2 is 1 and it satisfies 1 too. Thus, index 2 becomes our swap candidate. Finally, we swap the elements at index 1 and 2, resulting in the array 3, 1, 2. This is the largest permutation that is smaller than the original input array. The output for this example is 3, 1, 2. In the next example, we have the array 1, 9, 4, 6, 7. Again, we aim to find the largest permutation smaller than the input. First, we need to locate the rightmost point of decrease. Starting from index 3, we find that ARR 3 is 6 and ARR 4 is 7. Since 6 is not greater than 7, we move left. At index 2, we check if ARR 2 is greater than ARR 3, but 4 is not greater than 6. Continuing to index 1, we compare ARR 1, which is 9, with ARR 2, which is 4. Here, 9, 4 is true, so we identify index 1 as the point of interest. This completes the first step, and we now know the position where the swap needs to occur. The next step is to find the best candidate for the swap. Now that we've determined the breakpoint at index 1, we need to find the largest element to its right that is smaller than ARR 1, which is 9. Starting from index 2, we check each element. At index 2, ARR 2 is 4, which satisfies 4, 9. So, we set max_index to 2. At index 3, ARR 3 is 6, which also satisfies 6, 9, so we update max_index to 3. At index 4, ARR 4 is 7, which still satisfies 7, 9, so we update max_index to 4. After examining all elements, max_index is finalized as 4. We then swap ARR 1 with ARR 4, resulting in the updated array 1, 7, 4, 6, 9. This is now the largest permutation smaller than the input. The output for this example is 1, 7, 4, 6, 9. In the final example, we examine the array 1, 1, 5. To find the largest smaller permutation, we first look for the rightmost point of decrease. Starting from index 1, we compare ARR 1, which is 1, with ARR 2, which is 5. Since 1 is not greater than 5, we move to index 0. Here, ARR 0 is 1, and ARR 1 is also 1. Again, 1 is not greater than 1. Since no such decreasing point exists, we can conclude that the array is already the smallest possible permutation. Thus, the output remains 1, 1, 5. To summarize, the key steps involve identifying the rightmost decrease, finding the optimal element to swap, and performing the swap. If no decreasing point exists, the array is already in its smallest form. For edge cases, arrays sorted in ascending order will always remain unchanged, as no valid swap is possible. The time complexity of the solution can be understood by breaking it into three main steps. First, we need to find the rightmost element that is greater than the one next to it. This step involves iterating backward through the array, starting from the second to last element. Since we only make a single pass through the array, this takes n time, where n is the length of the array. Next, we locate the largest element to the right of the chosen element that is smaller than it. This step involves another linear scan from the chosen position to the end of the array, making it n in the worst case. Finally, swapping the two identified elements is a constant time operation, O(1). When we add these steps together, the overall time complexity becomes n plus O(1), which simplifies to O(n). The space complexity of the solution is determined by the amount of additional memory the algorithm uses. Since the input array is modified in place, no extra space is allocated for a new array. Instead, we rely on a few auxiliary variables such as I, max_index, and j to store indices and intermediate values during the computation. These are simple scalar variables that only require O(1) space. Importantly, the algorithm avoids using any additional data structures or creating copies of the array. As a result, the overall space complexity of the solution is O(1). The algorithm performs efficiently across all scenarios, but let's examine the best, average, and worst cases in more detail. In the best case scenario, the array is already the smallest permutation, meaning no swap is needed. Here, the first loop completes a full pass, and the function exits early without entering the subsequent steps. This makes the time complexity O(n) dominated by step 1. In the average case, the algorithm typically goes through all three steps, identifying the rightmost element, finding the appropriate element to swap, and performing the swap. Despite this, the time complexity remains O(n), because steps 1 and 2 each involve linear scans. In the worst case, the array is sorted in descending order, meaning we must perform full scans in both step 1 and step 2 before making a swap. Even in this scenario, the time complexity does not exceed O(n). Comparing the current solution to a naive approach highlights the efficiency of the optimization. A brute force method would involve generating all possible permutations of the array, sorting them, and identifying the largest permutation smaller than the given one. Generating all permutations of an array of size n has a time complexity of O(n), and sorting those permutations adds another layer of complexity, making it O(n). log n. The space complexity would also be extremely high due to the need to store all permutations in memory. In contrast, the optimized solution avoids generating permutations altogether. By directly identifying the previous permutation through a linear scan and a constant time swap, the current solution achieves a time complexity of O(n) and a space complexity of O(1), making it vastly more efficient than the naive approach. To mathematically justify the big O complexity of the solution, consider each step individually. The first loop, which identifies the rightmost element greater than its neighbor, iterates through the array once, resulting in O(n). The second loop, which finds the largest element smaller than the chosen one, also iterates through the array once, contributing another O(n). Finally, swapping the two identified elements is a constant time operation, O(1). When we combine these steps, the total time complexity becomes O(n) plus O(1), which simplifies to O(n). This analysis confirms that the solution operates in linear time, making it highly efficient for large input sizes.
Let's start by addressing some common mistakes when tackling this problem.
One of the most frequent errors is not identifying the correct pair of elements to swap. Instead of rushing to swap the first pair of elements that decreases from left to right, it's crucial to find the rightmost element that decreases and then locate the largest element smaller than it on its right.
This ensures the result is the largest possible smaller permutation. Another common pitfall is overlooking edge cases involving duplicate elements. For instance, in an array like 3, 1, 1, 3, failing to carefully handle duplicates might result in swapping the wrong pair, leading to incorrect results. It's also important to avoid unnecessary swaps. Remember, the problem explicitly states that only one swap is allowed. Performing multiple swaps or redundant operations violates this constraint. Finally, be cautious with arrays that are already sorted in descending order, such as 5, 4, 3, 2, 1. No smaller permutation exists in this case, so the array should be returned as is. Forgetting to account for this scenario can lead to errors like out-of-bound issues or incorrect outputs. Another mistake to watch for is confusing the logic of finding the next permutation with that of the previous permutation. While the next permutation involves finding the smallest larger arrangement, the previous permutation focuses on finding the largest smaller arrangement. It's essential to adjust your logic to match the correct goal. Now, from an interview perspective, there are key insights to keep in mind. This problem is fundamentally about recognizing patterns in permutations. Specifically, you need to focus on identifying the rightmost peak and swapping it with the appropriate element to maximize the result. Efficiency is also critical. An optimal solution should run in O(n) time, requiring only a single pass to identify the swap and a second pass to perform it. Brute force approaches, which generate all permutations, are too slow and should be avoided. Additionally, make sure to explicitly address edge cases during interviews. Scenarios like duplicates, already sorted arrays, or arrays with just one element can trip up many candidates, so demonstrating your ability to handle these cases will leave a strong impression. Lastly, it can be helpful to compare this problem to LeetCode number 31, Next Permutation, as it highlights your broader understanding of permutation-based problems. To further enhance your understanding, it's helpful to explore related problems that share similar concepts. The first is LeetCode number 31, Next Permutation, which asks you to find the smallest larger permutation with one modification. This problem is closely related and serves as a great comparison point. Another related problem is LeetCode number 1042, Flower Planting with No Adjacent, which involves making constrained modifications to an array under specific rules. Then there's LeetCode number 556, Next Greater Element 3, which focuses on permutations with constraints on digits, making it a good exercise to practice handling edge cases like numerical bounds. Lastly, LeetCode number 795, Number of subarrays with bounded maximums, while different in nature, requires careful handling of bounds and comparisons, which aligns with the precision required in this problem. Exploring these related problems can deepen your grasp of how to approach constrained array modifications efficiently. When solving this problem, it's worth considering the different approaches and their trade-offs. One naive approach is brute force, where you generate all permutations of the array, sort them, and return the largest smaller permutation. While this method is conceptually straightforward, it's highly inefficient, with a time complexity of O(n), making it impractical for large arrays. Brute force is only useful for verifying results on small inputs. A more efficient approach is the optimized single-pass method. Here, you traverse the array from right to left, identify the rightmost decreasing pair, and then swap it with the largest smaller element to its right. This method achieves O(n) time complexity, but it requires careful handling of edge cases to ensure correctness. Another variation is the two-pointer approach, which is similar to the optimized single-pass method but may offer a clearer structure in code for some developers. It involves using 2 pointers to locate the swap indices, minimizing operations while maintaining efficiency. Each of these approaches has its strengths and trade-offs, so it's about finding the one that balances clarity and performance for your situation. Great job following along. We've tackled the previous permutation with one swap problem and walked through an optimal solution. Remember, problems like this build your pattern recognition skills and improve your efficiency in solving array-based challenges. Thanks for watching.
and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!